So you want to create a game in assembly language for the Color Computer 3, huh? All right. Welcome. So if you have not been following the Color Computer Facebook group, you may not know this, but I have decided to create another game for the Color Computer 3. And I thought it might be interesting to let people kind of follow along on more of on a technical level, rather than just like, okay, I've got this animation in, hey, I'm doing these kind of things, but really kind of dive into some of the techniques in the code that's going to go into it. And so like this video and the ones that will follow are really intended to help you construct a game in assembly language for the Color Computer 3. I really it focuses a lot on the Color Computer 3 hardware, as well as the 6809. So that's really kind of the intent. It's not meant to teach you assembly language. I mean, there's plenty of material already available. I mean, you've got books, there's magazine articles, videos, a wealth of information that really already fill that gap. So I'm not going to be going too much into and trying to teach assembly language. I'm just going to simply assume that you have a basic understanding of the 69 instruction set, as well as the instruction side effects. Now, a lot of the terms that I'm going to be using, I do try to keep them kind of separate from certain things that might be confused with technical aspects, particularly in programming. And since we're going to be diving into that, and particularly within my own framework, I'm going to be using a lot of terms that may seem rooted in movie production. Things like scene, hazard, layer, actor, prop, obstacle, camera, framing, projectile blocking, and even some more specific terms like a pickup item. And I found that those work pretty well for discussing these kind of topics and keeping that kind of stuff separate from the actual technical details and the implementation of it. So we have some abstract ideas there. So like I said, I wanted to extend the Digger series to add more goals, obstacles, puzzles, but I also wanted to enhance the presentation. Now, admittedly, there's a lot that actually gets done in Digger, and there's a really good balance there between the sprites and the background animations and how those are used to actually give a really good presentation to the player. But this time around, I want to use some arcade quality graphics, and preferably something from an arcade game. The problem, though, is that Digger, just like Lode Runner that it's originally based on, allows the player to brachiate. And if you don't know what that word means, that's the moving horizontally on the rope. Now that's actually a pretty difficult animation to find. So that means that I would likely have to draw it. Because the only games that I could find that actually have something to support that are arcade versions of Lode Runner, and those just really weren't they weren't suitable. They just didn't really have the feel. They didn't have what I wanted to, and I could easily use those as a template. But that's also a lot of work, and I kind of wanted to get something that had it, so that wasn't going to work, and that was what I thought. But I did come across a game called Spelunker. In fact, in case I started with Spelunker 2, and then I ended up looking at the version that is now. Spelunker is a game that actually originated on the Atari 400 and 800 home computers. It was written in 1983 by a guy named Timothy Martin. So that was kind of where it started, but these were the arcade versions of it, and it does share a lot of the same gameplay, but it is really it's a departure from that original game on the Atari. But and it's a really basic game. It's a platform game where the player descends into this very large, this very deep cave that is divided into 6 different stages, and the goal is really just to collect treasure while avoiding obstacles and working with a limited amount of air. In fact, it actually shares some gameplay with what is it, Mine Rescue, that Steve Bjork did after it was sometime it had to have been 88 or 89 because it used the same engine as Super Pitfall. And so the cave, and really what we call the tile map, includes a lot of hazards. Includes bats that drop this guano on you that kills you. It's got steam vents, and it's got this ghost that comes out occasionally to take you to, I think what the thing was the shadow world, I think is how it was described in the box. And so looking at this game, looking at the Spelunker 2 has the break gating, so that takes care of that animation. The characters, it's a good good sprite for the character. It just needs a little bit of recoloring, but yeah, it's a really good sprite. And the overall feel of the game was really similar to Digger, except it just didn't have the digging. It had jumping rather than that. But and it's not focused on things like ladders, and you don't have anything chasing you. So there's really only a couple of differences in the game mechanics. So I figured, well, why not do something that incorporates the gameplay of both Digger and Spelunker, using the graphics from like the arcade version, and maybe adapting the tile map from another version, maybe even the original Atari version. I mean, both games would utilize the same graphics and sound, maybe with a little bit of variation for the digger part, so that you'd know where you can and can't dig. But each would represent a different mode of play. So the first would be, something like adventure mode, where it'd be a CoCo specific version of Spelunker. It's cave exploring, it's just you against the environment, for the most part. And the second would be challenge mode, which would include the digging, the break-gating, collecting gold. As a goal, which would continue the Digger series, you'd have things chasing you rather than just, you against the environment, you against the environment and the gummers, and trying to get all the gold, making sure that you get that. And that was, and I started thinking, that could work, but there's some challenges there, because with Digger, I have a lot more control over a lot of it, how the presentation, how big the levels are, and how the chasing and all that works. It's a departure from Lode Runner. It doesn't try to be Lode Runner anymore. But with Spelunker, throwing that into it, there's a lot more constraints and things that I have to consider that may not be necessary for Digger, but would be necessary for Spelunker. So I figured I'm gonna have to do something. I'm gonna have to gather some technical details. I'm gonna have to look at the different versions of it for sure. Probably need to maybe allocate some CPU resources, because this is going to be a pretty demanding game. Memory-wise, this is going to be kind of a nightmare. So picking that memory model, certainly, and getting a because of the size and I'm expecting this to be very challenging as far as getting it to fit into memory. Defining a memory map for physical memory, so that when I do start developing, I know where this stuff is going to go, and I know that I'm going to be able to fit it into it. I know that if it's not going to fit, then I have to come up with some kind of a solution for that. And the same thing goes for logical memory. That address space that the 1609 accesses, that whole 64K, that logical memory. You've got 8 MMU slots. Each one represents an 8K block within that address space. You can map things in and out. You're going to be doing a lot of different types of operations. So there's a lot of stuff that you need to map out, and some of it you don't have to map out right away. You don't have to do anything like that. But there's a lot of other stuff that you might be good to know ahead of time. And I figured this time it would be. So now, the rest of this discussion is going to revolve mostly around the Spelunker part of the game. I mean, it's the primary influencer for these requirements. That's why I'm going that extra mile and collecting some information that I might not necessarily have to collect or need to collect it before I get started. And one of that was looking at the different versions, because for this there are 6 different versions of the games, which can be kind of divided up into 4 different kind of generations. So you have the original version that I mentioned on the Atari 800 and 400, and that came out in 1983. And shortly after that, it was ported to the C64, and I think that one was released in 1994. Now, those two games are pretty identical. The only real difference that I could tell was some coloring because I mean they're different computers. They've got different palettes. Although the sound did actually sound identical, so it didn't sound like they did anything special for the C64. So that's kind of the first generation, and then the second generation is the arcade version. We're gonna be talking about both the first and the second one at times. And this is a variant of the original, and it does have modified gameplay. And it does depart from a lot of the things in the original, Atari and C64 versions that really made it a fun game, really made it a home computer game. But there's things in this that are meant for the arcade. They're meant to steal quarters, and they're just not things that we want to include on this. So we're probably just going to be using the graphics from that and not their tile map, not their world. Okay, so and then there's the third generation, and that's the MSX and the NES version. These came out in 1985 as well, the same year that the arcade version came out, and they're actually a little bit different, but they do retain the gameplay, the game mechanics of the original, but they're scaled a little bit differently in places. So, and we will be referencing that because they've got a really, really nice in-game music for that. And that's really the only thing that I like about these games. The in-game music is really catchy. So we want to keep that. So the MSX and the NS versions will probably come up from time to time, and especially in reference to the music and sound effects portion of it. So anyway, the last generation 4 is excuse me, a much more modern version called Spelunker HD, and that was released on the PlayStation 3 in 2010. I think that was the North American release. I think it was released in Japan in 2009. Now there are a couple of variations of that game. I think Spelunker World and Spelunker Party, but we're not going to be referencing those. I don't even think they're active anymore. I think you can play them. They were online social versions of the game. But yeah, so and the interesting thing about that game is that even though it's presented as a in 3D perspective, and it does a really, really good job of it too, there's also a classic mode which uses just a regular 2D tile map, uses graphics very similar to the NES version, and the tile maps are the actual maps that you play in 3D mode, so you can play too. So there's always the possibility of taking some of that from the PlayStation version. And that stuff isn't available on the internet, so I have to do that kind of by hand. But there is a possibility of that because the PlayStation version has 10 areas, each one with I think 5 or 6 stages, and it may vary. But the size of those vary, so it's something that I'm going to have to approach with caution because I think that's going to be a big problem coming up. So now an interesting tidbit, and I think I mentioned some of this in one of my Facebook posts, is that the NES, the MSX, the arcade, and the PlayStation versions were all done by a company called IREM or IREM. It's IREM. They also did the arcade versions of Lode Runner, which is what the Digger series is based on. I think there's like 6 arcade versions of it, although I think most of them were released only in Japan. And so there's actually kind of that connection. And another tidbit is that Broderbund was the company that released both Spelunker as well as Lode Runner. And of course, Spelunker 2 really does kind of have that brachiating, which gives it that Lode Runner kind of feeling in some instances. So we'll see how that works out. So then I need to start taking a look at some of the technical details because we're going to be taking stuff from 3 different versions. Now the music doesn't really concern me too much because that's going to be a problem all in itself. So that's something that I'm going to address at a later time. I'm probably going to devote a whole video to it. But because we're taking the graphics from the arcade version, which is presented at kind of a different scale, but using kind of the tile map maybe from one of the other versions, instead to kind of retain that that same gameplay, then there's a lot of things to consider. And the resolution is actually kind of tied to that, because in most of these games, it's except for the PlayStation version, the tile map is 2 screens wide. Now the MSX and NS version, I think, are a little bit slower, so you share a couple things, but so that's directly tied to the display resolution. That determines how much you can see on top and bottom. So that's some things that are going to need to be considered. So I'm going to start off with something like 320 by 192 and kind of go from there. And the reason why I'm choosing that resolution is a couple of reasons. First, we're going to have four-way scrolling. That I can already we already know that. So that kind of requires a whole lot of memory on the CoCo 3. So there's going to be some tight stuff. So keeping it at a reasonable resolution is going to be important. So then I'd take a look at like frame rate. There's you start to lose things and start to have to make more adjustments the lower the frame rate you go. That travel distance, that tempo, all of that is very important. And I think the MSX and NES version of Spelunker, I think, are a really good example of that, because the MSX version is noticeably slower than the NES version. And the thing that I really love about it is that even though it's noticeably slower, they reduced the tempo of the music, of the in-game music, to match. So you actually get that kind of that tempo helps you out. So it makes it a little bit better to do it. But in our case, we know that we're probably not going to be able to achieve 60 frames per second here. That's just out of the question. I mean, when you look at just the arcade version, that presentation, it's just not going to happen. I do think that shooting for 30 frames per second is absolutely achievable. Requires a bit of work, though, and unfortunately, I think that there are going to be some sacrifices in both the way of memory as well as cycle consumption that are probably going to drop us down to 20 frames per second. Now, that's not terrible. I do prefer 30 frames per second. I have no problem doing 20. I think it's certainly acceptable for a lot of games, but that affects our scrolling, that affects how we scroll, that affects our travel distance, and a lot of that. So keeping up that tempo in the game is important. Of course, we are working with a game coming from the Atari 400 and 800, which does itself run at a lower frame rate, or at least appears to. But the arcade version, of course, which has the presentation we're going for, runs faster. So we've got to find that balance there to work it out. So yeah, I'm hoping for 30 frames per second, but and it's going to become clear whether I can achieve that, pretty quickly, whether I can achieve that or not. So probably within the second or third video, we'll probably be figuring that out. But may have to fall back to 20, but that's acceptable. Anything below that, I definitely recommend that you don't do. But this is good. This is important because I guess it depends on how you look at it, because if you choose a particular frame rate, or you're trying to achieve a particular frame rate, that's going to dictate how many cycles you have to consume for everything that you want to do. Now, if you take it from the kind of the opposite side of that, it's like, well, I'm going to use as many cycles as I need, and that's going to determine my frame rate. I think in most cases that when you do it from that side, you say, I'm just going to use as many cycles as I can, and frame rate be damned. I think that gets you into more trouble than kind of going the other way. I think it's more manageable when you go when you just try to pick one. But certainly up to you. But it's something to think about, because that is tied to a fair amount of things that your program is going to have to do. So of course, like I said, there's scrolling in this. And of course, there's actually two different methods of scrolling in this particular game. You have smooth scrolling, in which case the player moves around and the screen just scrolls, follows them along. And then you have auto scroll, which is how the original Atari game or version did it, and that when the player gets to the very edge of the screen, it scrolls the whole screen over. You just jump to that whole next screen. So I'm really not fond of that approach. I do like that smooth scrolling, but that's going to require something like some camera, some algorithms to follow them around. Get that follow just right. That arcade kind of follow thing. So it's we'll see how that goes. That's something we'll probably take care of not too soon. We know that we're going to be doing full screen scrolling. In this case, 8-way. We expect that there's going to be diagonal scrolling, so we consider that 8-way, which is something that has to be taken into consideration because you're not drawing just one edge. You're drawing two edges. You're drawing the right edge, bottom edge, or the right edge and the top edge. So those are going to consume cycles. So those are going to again affect what frame rate you can achieve. Now, and here's the thing: since we're doing full screen scrolling, we're going to use the logical display mode. Now, I'm sure there's a lot of names out for it. I refer to it as logical display mode because that's what it is. Now, this is a special mode that the Gimme supports that gives you a frame buffer that is 256 bytes worth of pixels wide. Okay, so of course in this case we're doing a 320 by 192 physical display with 16 colors, which is 2 pixels per byte. So math time, what you have is a frame buffer that is 512 pixels wide, but you can only see 320 of those pixels at any given time. So you can scroll that screen, left and right, horizontally, and that's how we achieve contiguous scrolling. I'm going to go into that in a little bit more detail, and that kind of description sucks a little bit. But at this point, it's the only real thing to know is that it's important because of how much memory it takes. So a 320 by 192 display usually takes up, in 16 colors, usually takes up 32K, a little less than 32K. This is going to take us up to 48K, solid 48K. You can't escape that. That's the price of of getting that full screen scrolling, and we're going to need a few of them probably, and which takes me to the next point of why, which is we want the horizontal scrolling to work or to happen at 2 pixels per frame or 2 pixels per update, and that's important because the Gimme chip does not directly support that. The Gimme chip will actually only let you scroll in 4 pixel intervals, where we want to scroll in 2 pixel intervals. So now we can fake that by using additional frame buffers and then offsetting whatever we draw to it by 2 pixels, and so we call them even odd buffers. But the problem is that now we require more frame buffers. Now at 48K, you're doing double buffering. That's another 96K at least. And then of course we haven't even gotten into the overflow and stuff for vertical scrolling. So we already know that we're going to be taking up a ton of memory for this game, and we haven't really even gotten started. So and we also know that the display only scrolls when the player is a certain distance from the edge. So that's that camera stuff that we want to get. Now vertical scrolling is going to move at a fixed rate of either 2 or 4 pixels. I guess it could scroll at 3. We have the option to scroll in 3 pixels, but it'll probably be either 2 or 4, and that's again is going to be tied to our target frame rate, because if we go to something like 20 frames per second, we will probably scroll at 4 pixel intervals, whereas at 30 we'll probably scroll at 2. So again, that travel distance, that kind of thing is going to be important. So at least may not need to know that right now, but we will, and we don't want to forget it. So, and that is really kind of the easy stuff. That's normal stuff. But the assets are really needed to take a look at, because we're going to pull stuff from three, maybe 4 different generations of the same game, each with their own requirements and differences and all of that. And so it's there's going to be a lot of work to first get this into memory, and to get it working in the same manner as the arcade game, for the mechanics that we're going to support. And the sprites are the tiles, the tile maps. All of this is going to really impact us, and so we're going to have to make sure that hey, we can fit it in memory, and 2, we can manage this. So the the sprite graphics are going to be sourced from the arcade version of Spelunker 2. That's pretty well set. We're going to do a bit of recoloring on that, but nothing outside of that. Probably use the same colors from Spelunker 1. Now the player sprites and the tile groupings, which we'll get into in a minute, are going to be framed in a 24 by 24 pixel block. Now, and what I mean by that is that if you look at first the sprite for the Atari and the NES versions, they're within a 16 by 16 pixel block. And when you look at common platforms within the game, the terrain that you walk across, they're 2 tiles high and 2 tiles wide, framing a 24 or a 16 by 16 pixel block. Now, and all these games, by the way, have 8 by 8 pixel tiles, so that's all good, or the equivalent. Now, the arcade version everything is framed at 24 by 24 pixels. So we're actually going to have to scale things up, at least as far as like the tile map goes and the world, how it's laid out, by 50% in order to match that different those 2 different sizes. And because if you try to use that 16 by 16, I mean, everything is scaled down. The passageways, the ceiling, the height of the ceiling, and all that is meant for a 16 by 16 pixel actor or player actor in the game. Whereas the sprites are now 24 by 24, so you've got that extra thing that's going to get in the way. You're going to have to make modifications, and it's going to be very, very different and probably awkward in a lot of cases, especially when it comes to trying to jump off of small ledges. So that's going to be one of our bigger challenges. That's definitely going to be one of our bigger challenges. And of course, the player sprite has 80 frames at 24 by 24 pixels, so that's a lot. Moving both ways, jumps. So some of that's going to be reduced. There's actually some sprite frames we're not going to need because we're not going to be doing certain things. But yeah, that's going to consume a fair amount of memory. Now our tiles, of course, are going to be 8 by 8 pixels. We're going to match that to the arcade version, so that we get that same granularity with the tiles, and we can actually match that difference in scale for the tile map. That's going to be big. Now, if you have seen the post on Facebook, and I'll throw some stuff up here, the arcade version, its presentation is very rich in its graphical in its graphics. You got your background repeating, which is a bit larger than like in on the CoCo we might just use 1 tile. Like in Digger, I had 1 single tile that I used for the background, and then some specialized ones for the parallax. But in this particular case, because we have uneven terrain, uneven walls, all of those variations, all of the variations with the pickup items that we may want to have as tiles instead of sprites for saving CPU cycles, all of that comes out to a little less than 1,024 tiles. That's a lot, but they're only 32 bytes each, so it's only 32K, but it is a lot, and it does increase the size of our of our tile map by another 50%, because now you have to use 2 bytes per tile, or you could possibly merge them together and extract them, but that's CPU time. But the raw tile map is increased by 50%. You're using 2 bytes instead of 1. Now the tile set graphics are going to be sourced from the arcade version of Spelunker. So I've already got that already kind of handled. I actually wanted to get that done sooner rather than later, simply for the fact that I wanted to know what I was up against. And here's another example. There's a guy, I believe his name is Cedric. He's wanting to port, or he's working on porting a game called Rough and Tumble from the Amiga. And this, I think, is an early 90s Amiga game, so it's actually richer, has more requirements. Now the tile set for that game is 16 pixels by 16 pixels. so it's 128 bytes per tile. But the tile set also has 800 tiles in it. So I only have like a couple hundred more than that, and that's it. So and I think that comes out to like 800K, or I'm sorry, 100K for that just for that tile set. Now, here's the thing: that's not the only level that has its own graphics. In fact, every level in that game has its own tile set. And those vary in size, so you know that it's at least 800 tiles, so it's going to be at least 100K, probably a fair bit more for some of the later levels. So that's stuff like that is going to be challenging because some of the levels you can reduce the detail on, and in fact, we're actually going to take a look at that here in a second too. So, but so like with Splunker, I can reduce some of the detail. I can get rid of that textured background. Just have it black. It's perfectly acceptable for a CoCo game. In fact, it's actually kind of growing on me. It's really is growing on me. Originally, I was kind of dead set on having that textured background, but that black background is really appealing. It's starting to grow on me. So there's a lot of challenges with just getting this stuff in memory, and he's not going to have that luxury with all the levels. Some of them, sure, but some of them you're not going to have that luxury of being able to completely reduce that background without kind of destroying that feel and that presentation of that particular level. Something like that requires a lot of changes in the art, and it takes a very, very concerted effort. You can't just convert art over or expect to just convert art over from another game or from that game and try to use it. You actually have to go in and change some stuff. So now the levels and stages, I figured I'd start looking at it, as a variation of the Atari version. Now I do have a complete map of that particular game. It's for the C64 version, but as I've been told, apparently there's really no differences between the games, so that's what I'm going to go with. So yeah, I've got all of the level data. I know how it's divided up into stages. It has 6 different stages. But knowing that, I also know how big it is, and that's going to hurt. That is going to hurt. So even dividing it up. Now, in-game music is most certainly going to be for a PSG, unless I were to go to 2 megs, because I wouldn't be able to fit the samples in. I'd be able to play the music, but I wouldn't be able to actually fit the samples into memory. So in order to get in-game music, I'm gonna bite the bullet and just support a PSG, or at least a couple of them, like the AY chip and all of that. So, but the sound effects, I'm hoping to get in waveform base. So they'd be digital sound effects, but if I can't fit those into memory, then PSG will definitely have to be. It's definitely an option. I mean, I'm not saying it has to be used, but it's definitely an option. So I want to keep this a 6809 game. I want to keep this 512K. There's all kinds of things that I really, there's a boundary I do not want to cross. But some of those decisions and some of those wants for me may not be possible because if you look at the tile maps, now the Atari version is pretty big. It's 80 by 388. 80 tiles by 388 tiles. Now, of course, because of the resolution that it uses and everything, that's 2 screens wide, 320 by 200, so it's a 640 by whatever. And I think it comes in like a little like 31.5K or something. Very, very impressive for an 8-bit Atari. 64K is all you got. Impressive, actually. But then you've got the arcade version. Of course, the same thing there. It's 2 screens wide. Of course, the resolution for that game or the display resolution is 384 by 256. So yeah, it's nothing we're gonna really be able to do. But it has a tile map that is 96 by 512, and that's actually a pretty good size. Now the 3rd generation, the NES, MSX versions, they've got a really small tile map. Actually, that's 56 by 302. Now, of course, both of those platforms have a smaller resolution. The NES is 256 by 240. even though for NTSC I think it's only like 224 scan lines are visible or really usable. So that's actually a lot smaller than the original. So and of course I'm sure that was done to fit it into the tiny ROM that they have. But at the same time, I really don't like the level layout. It seems like they've cut some stuff out that they probably shouldn't, or just shrunk it too much. Um, so in looking at the Atari version, and if you've already pulled out your calculator, or if you're really good with math, and you probably figured out that the CoCo tile map, in order to scale up, to meet that arcade presentation, that 24 by 24 pixel framing is going to be 120 by 582. That's pretty big. And I mean, you have to understand that's 138K just for tile data. Now, if you were, I mean, you could certainly divide that up into the various stages. Just use just those stages, and get it down to something like 120 by say 136, which would fit in 32K worth of space. But there's this. The game has this transition as you go from one stage to another. It's a very smooth transition. You don't leave the game. You don't load a level. It just goes. You as the player go on to it. It's really an awesome presentation. We'd like to keep that. So that's what we're going to start with. We're going to start with that, and we're going to see where we're going to have to make sacrifices, and what solution we can come up with to either achieve that or cut it down to something more reasonable, which, I mean, that's going to be a last resort for me. So anyway, so moving on now, I really needed to consider, because those requirements are pretty hefty for the CoCo without scaling them down. And yes, I'm going to have to make sacrifices, and we'll be talking about that in the next video. So first, I needed to decide which CPU am I gonna write this for. I mean, doing something for the 6309 is vastly different than for the 6009. I know it's the instruction set is a superset, but the instructions that you have, the registers that you have, everything about that chip, you're going to write things differently, or you should be writing things a lot differently for a lot of what you do in a game. It's very helpful and incredibly optimal for your game. You can achieve a lot, but you also limit your user base. Of course, now you do have the 69, and that's what I'm striving for, and I'm going to be measuring things and deciding what to do, before I really start getting into the game. But yeah, that's it is something to think about. I don't necessarily know that I would recommend writing for the 6309. I mean, don't get me wrong, it is a wonderful CPU. I'm very familiar with its instructions, with optimizing for it, and there's a lot you can do. Even when you get past like the TFM instruction in native mode. I mean, once you get beyond even that cheap stuff, the cheap thrills that you get, when you get into actually writing real code, and complex code, those instruction sets come in real handy. But it is a very different beast, and you really do have to target it. So if you're looking at it for just like native mode or the TFM instruction, to be quite frank, the 6009 may actually be a better choice for you. I know it would be a bit more challenging. You lose certain performance, but then you have to decide how many people are really going to be able to do it. Does it really reduce the amount of work that you have to do? I mean, yeah, the answer is yes, it does. So you do have the things like that to think about, but you got to decide in the end which one you're really going to write for. So of course, the next thing is that I'd recommend is after that is defining general usage for your registers. There's and more importantly, be consistent with their use with that usage, and trying to kind of stick with those kind of arrangements and their preferred usage, because this comes in really handy, especially when you have to do whole program optimizations, or you come back to the code later and your code is still just as optimal. this kind of thing doesn't change how how optimal your code. It doesn't decrease the optimizations or anything, or the ability to optimize. But getting an idea of what your preferred usages can make grokking code a lot easier. And I have a basic thing that I follow, and it's really reflected in the framework that I created. The framework called Chaos. So I'll share that here with you, just in case you haven't done it, you haven't really thought about it. So I allocate each register based on their general traits, and a lot of it is really easy. A lot of it is just pretty obvious. But being able to communicate this with other people who may look at your code, or people who may follow it later, aren't necessarily in tune with that kind of thing, can make it a little bit easier. So here's the way that I arrange my register usage. First of all, is the Y register. Of course, we use that as a source and destination address and counters, for indexing off of stuff and accessing data. Now, I prefer to use the Y register as the address for my primary data structure that I'm working on, or the active data structure, you might call it. Now, you see a lot of the programs that, or a lot of the functions that I write, a lot of the code that I write is bound to an instance of a data structure, which means that it has to have the address of it in order to do what it needs to do with it. And of course, these are all functions, and all code is meant to work on different multiple instances. So there's no real shared data, so you actually have to be able to access it through an index register, and this is the one that I've chosen to do it. And I have found that it is incredibly helpful in optimizing your entire game loop. It comes in very handy in using it that way. Now, the X register, use it as a source and destination address and counters, and certainly prefer it when a comparison of that register is required, or even desired in some way. The X register, that comparison is going to be one cycle faster than any of the other comparisons. So you want to keep that in mind. Plus, you have the ability to add B to X. Now, of course, there's the U register, which is a stack register. Now, I'm not going to get into the S register here. That's very special use case, and I'm going to be covering that in an entire video. So we'll wait on that one. But for the U register, I use it as a source and destination address, and I prefer it when data can be transferred using stack operations. Now, I don't use this for counters unless absolutely 100% necessary. There's no alternative, simply because that the load effective address instruction for U and S for the stack registers does not modify the condition code register, so you don't get that. Well, hey, we know it is 0, so you have to do a comparison in order to get that, then do your branch. So we try to avoid that. So I just say I don't do it at all. Now, of course, A and B used for math, counters, bit manipulation. They're accumulators, and of course prefer B when it can be added to X. So you want to think about that. And then there's the DP register, which I use for accessing common application data, as well as accessing various buffers during the game loop. And I use that for things like blitting and all of that. And then there's the CC register. Now, I don't use the whole register. I just allocate the one bit, the carry bit, and I use that to return success or failure status from functions, so that I don't have to waste or spill or reload a register. It makes it very easy to do or to use. So there's less hassle and less overhead in dealing with that kind of stuff. Now, the dealing with CPU cycles is something that I really did need to consider this. So I mean, you've heard about the requirements. We've got we've got a lot of memory usage. We've got a lot of sprites. We will certainly try to trim that down, but at the same time, it's going to require a lot of memory. We're not going to have probably not going to have the option of using compiled sprites in this particular game, which is certainly disappointing. I'd like to try to find a way to, but it's unlikely. So I have to face the possibility, the strong possibility that that's going to happen. So frame rate became a little bit more important than it normally would at this stage. It's certainly something that I do keep in mind throughout, and I measure, and I test to work everything in there. But at the same time, this is not something that I usually do this early on. But in this particular case, it is. Now, for those of you who don't know, who don't really think about it, the CoCo 3 running at full speed executes at, actually I only have the megahertz down here. Let me see if I can remember this. It executes 1,789,477 cycles per second. I think that's right. Okay. So now, of course, we can all we have to do is divide our frame rate in that number, or divide this number by our frame rate. Hey, we know how many cycles we're going to have. And when you look at something of 60 frames per second, that's 29,824 cycles. I don't think that's really going to get us to where we need to be. We've got we've got scrolling, so we're going to have to draw the edges. That's going to take some CPU time. We've got a few sprites on the screen. They're 24 by 24 pixels, so we know that's going to take some. Probably not gonna make it. 30 frames per second. We've got 59,648 cycles per frame or per update to do our thing. And that's a little more I think achievable. Because we'll certainly have to manage that in order to achieve that. That's something we will have to pay attention to, but it's definitely something that is achievable. Now, of course, 20 frames per second, we've got 89,472 cycles. So that's actually a lot. And if you look at something like Digger, which has got a lot of the stuff that we're going to need to do in this game, the horizontal scrolling, vertical scrolling, although it doesn't do contiguous vertical scrolling, which you do have to deal with here, and we'll cover that. So it does reflect on it, and there's a lot being done in that game. A lot of background animations. It's got parallax animations. There's levels that have 9 sprites on the screen at one time. You've got digital music playing, so there's a lot that's going on in that game. So there is a lot that you can do with that. So I think that's going to be my cutoff point here. That 20 frames per second, I'm pretty solid on that. But there is a lot you can do. But there are a lot of things that really eat into that. So when we look at that, I like to kind of divide those cycles up. In this case, we're gonna start with 30 frames per second. Well, that's what we want to do. But I've got to kind of allocate that to some things that I know are going to be happening, so that I know where I stand. I know what my goal is, and I know where that boundary is, so that when I start hitting it, and I start seeing skipping frames or audio that isn't maybe playing the way that it should be in certain circumstances, that I've got a frame rate problem and I'm going to have to address it. So this kind of helps me on track. So and I do this because some of these numbers are very solid when you go into it. Some of them not so much. So what I like to do is I like to split the number of cycles that I have, and in this case it's a total number of cycles is 59,648. So we're going to be basing all of this stuff on this one. What we're going to do is I'm going to divide that up for 3 different tasks that are always going on in my game loop, and I'm going to start by giving 50% of that to my rendering. That whole rendering part draws the sprites, the edges, all of that. That's 50% of the CPU. That's where we're going to start. That's where we're going to start now. And at 30 frames, that gives us 29,824 cycles to work with. I still thinking that's achievable, kind of. Now for sound, we're going to give the sound 25%, and that's a solid number. And that's 14,913 cycles. Now that number is based on a playback rate of 7.68 kilohertz, and mixing 2 buffers or 2 samples and sending them out to the 6-bit audio DAC, or the audio port in the CoCo. So this is fully CoCo. It's and you're looking at I think it's roughly 22.5% for one channel, and 24.5% or 24.25% for 2 channels. That's something that we want to get. That'll if we can, that's great. If not, if we have to use one, we're only going to gain a couple percent. So the only really way that we can gain anything truly significant from that relative to something like rendering is to reduce the playback rate, which we're going to try not to do. So we're going to keep that at 25%. And then of course the remaining goes to the game logic, and that's 25%. Now, a lot of this game is probably going to end up being, at least for as far as managing um, the pickup items and all of these other things that appear in the world, and making sure they're animated at the right times. Remember, it's 120 by 582. Got to manage stuff all through that. And so, but even though there's going to be a lot and a ton to manage, I do not believe that I'm going to need more than, say, between 15 and 20%. But I'm going to keep it at 25 right now, just in case, because there is going to be a lot of data, or a lot of data that has to be processed, and a lot more that doesn't. Being able to optimize not doing that is going to be a challenge. Now, when it comes to rendering, I start with the 50%. It gives me enough for game logic. My sound is pretty solid, and for the most part, I've written enough blip routines, just like you will, to draw that. I've got actual cycle counts, so I know how this goes. I know what the performance impact is going to be, and so I'm going to try to break it down for those who, maybe this is your first game, maybe you haven't gotten into optimizations yet, or blitting yet. Maybe you haven't gotten that far. So essentially, what you do is you've got really three steps. You determine the address or the location in the frame buffer that you're going to draw that sprite to, and you take that address and you put it into an index register. And then you determine, which sprite you want to draw, where it's located, and you take the most significant byte of that address and put it into the direct page register. And then what follows is an unrolled loop that blitz, a sprite using a mask. As we want to mask stuff, and draws that. Now, and that, in fact, I'll step you through that one too. So that process of drawing that sprite and mixing it kind of runs like this. You load 2 bytes out of the frame buffer into D, and then you apply a bitwise AND against the mask data in order to remove the pixels that you're going to replace. Okay. Then you do a bitwise OR in order to mix in the pixels of the sprite, and then you store those 2 bytes back to the frame buffer. And that takes about 1,700 and I think it's 10 sprites, or 10 cycles. Sorry, 1,710 cycles for that blit, and it does that 64 times. That load and or store does that 64 times. So it does take a lot of time to do, but 1,710 cycles is actually pretty good. Now, if you have to use an index register instead of the direct page register for the address of the sprite data, that's going to consume, I think it's like 254 cycles more. Yeah, it's 254 cycles more. It's going to consume 1,964 cycles. So now the interesting thing here about using an index register versus the direct page register is that if you were to, say, run this on a 6309 and run it in native mode, okay, if the version that uses the index register for the sprite data would, I think it's like 15 cycles, that's 15 cycles faster, whereas on the version that uses the direct page register, that's 262 cycles faster, something like that. It comes, and if you optimize, of course, if you optimize it specifically for the 6309, it comes out to 1,230 cycles. So it's I kind of know where I stand now. I don't have numbers readily available right now for the 24 by 24, but it's pretty easy to calculate out. You're doing just loads, stores, ands, ors, the occasional load effective address for the frame buffer, in the address that's in the index register. But other than that, it's pretty straightforward, and it can be done pretty optimal. Now, of course, you have to also consider that that's just the part drawing, that sprite to the screen. It's not that those cycles don't include how the operations to calculate on the frame buffer or select which sprite. That's completely different. That'll vary depending on your implementation. This is just the part that draws it. So you also have to restore. Remember, you also have to restore that area, that dirty area that's behind it. So you need to account for that when when you're determining, hey, I've got my sprite routine. It draws at say 2,000 or 2,500 cycles. Maybe you're doing bigger. Maybe you're doing more data. Or even in this case, 1,710 cycles, but it's going to be another 1,800 cycles, 1,700 cycles, 1,600 cycles, maybe, I don't know, to restore that. I don't have my cycle count for that one on hand. I really wish I did. But so you've got to be able to, and if you don't have it, you have to be able to reasonably estimate. So let's just say it's twice as much, 3,420 cycles all the way around for drawing the thing, calculating the address and all that. 3,420 cycles. If we want to draw 8 of those, well, that's 27,360 cycles. Okay. Now, at 30 frames per second, hey, we've got a couple thousand, 2,500 cycles to go. We're right in there. But of course, wait a minute, we have to do scrolling. So, and that's, I guarantee you, going to be more than 2,500 cycles. So yeah, this even though I've only got the 16 by 16 pixel stuff here, because that's what I had been considering all along, or up through most of it was 16 by 16 versus the 24 by 24. So anyway, if that you're talking about 50% more data. I mean, just overall, you're drawing a lot more, and so if I have 5 sprites on screen, that's a considerable amount of sprite to be done, and we're going to exceed that 30 frames per second. So that's something that we're going to have to something's going to have to be considered later on, not now. So now next is to take some of that, and I've got to create some memory maps so I know where stuff is. Now what I am planning on, I'm going to start this off with everything that we've got, all the raw stuff. So we've got a tile set, 1,024 tiles, 8 by 8 pixel tiles, so it's 32 bytes each. So that's 32K. Not too bad. We're going to stuff that in the very beginning of our memory. Oh, and did I mention we're going for 512K? At least that's the goal. So now our tile map, raw tile map, 120 by 582, 2 bytes per tile. That's 144K. Okay. Remember, we have to do this in 8K chunks. So we've got some left over. We can probably find a use for that later on. Not a problem, but it's still 144K. That's coming up. Our memory usage is growing really quick here. Now we've got sprites. So we know we've got about 80 sprites in there, probably a few extras. We'll be able to tone it down, trim it down some, but that's going to be taken out by the things that the other things like the ghost and the bats and all of that. So we're just going to say 80 sprites, 24 by 24 pixels with a mask. That's 48K. Yeah. Now we're already at 244K. We're at almost half of our memory. And well, in fact, we're I think a little bit beyond our amount of usable memory for this game. So now we've got our frame buffers. Now we've got the top 64K is allocated to something else. We can't change that. So the frame buffers have to fit in everything else, and we've only got 224K left for that. So that's what I've got here now. With that amount of memory, I can do contiguous scrolling on the vertical axis, but not if I use even odd buffers, which would allow me to scroll 2 pixels or in 2 pixel intervals on the horizontal axis. So something is absolutely going to have to give here, and I think at the end, I do believe in the end, a lot of it is going to come down to frame rate. I do believe that at this point, in fact, actually thinking about it, doing this video, that 20 frames per second is probably going to be more realistic than 30. So, and I guarantee that will be something I will be taking up in the next video. I will be doing some super awesome math, scoping some stuff out, and getting some code together so that we've actually got some things to actually do. So now after the frame buffer, we've got well, what I call chaos DOS. It's just a basic file system. It's really just a disassembly of RS-DOS with the file I/O and the discon stuff in it, and I'm actually phasing that out. But this particular 8K block is also used by BASIC. So we have to keep our kind of file system stuff here, even if we don't use our own, because if we're using like something out of ROM, then then we're gonna, some of its file or some of its buffers and some of the data that or memory that it uses is going to be in that region. So we want to keep that open, and we want to keep our own stuff in there. And right now we've got more than enough space for our file system, for our file buffers, and of course when those are phased out, we'll have probably even more space in there. So this is where I stick a lot of stuff that I just need to get it somewhere out of the way. It's really, most of it's non-essential to the game loop. It's needed in context where we actually have more control over what we can do with memory. So we're not. it just does make things easier to put in there and just map it in and out as necessary. So then the 8K after that, we're going to stash our chiptune player, our track data, and our instruments. So we've got all that covered. So if we end up not being able to do digital samples, then we'll have this completely taken care of. And then of course we've got 16K of reserve space. I don't know what I'm going to use that for, but I have a feeling it's going to have something to do with collision detection with the terrain, with the platforms. And then after that we've got some game code and data, and which is 16K. Followed by shared data, and this is actually a very, very important area. This is one of the slots of memory. This is always mapped in no matter what. Shared data is always mapped in. It's used with the next 8K block, which is the chaos runtime, another 8K. So it's shared between the chaos runtime as well as the game application. So, and this is actually kind of important because the chaos runtime does very little modifications to the data in there. It's simply a communication buffer. The game stashes all of its in shared data data that needs to be shared, and it tells chaos what to do with it. So a lot of times it means mapping in other stuff and mapping out the actual game in order to accomplish it. So that data has to be accessible by chaos. So that's where that's going to be. Now the logical memory map, for the 64K address space is actually a lot easier for me. A lot of the stuff I already have defined. So some of it I'm going to share with you, because some of it you will actually get you thinking about how to arrange your program and what options are available to you. Now, in this case, you have to understand that the gimme has 16 registers for selecting an 8K block, mapping it into the address space of the 16 or 9 different blocks in physical memory. So they can be mapped. They can be mapped into multiple slots. They can be mapped out of order, whatever. Now it has 16 registers, but only 8 of them are only ever used at once. So it divides these into 2 sets of registers for what it calls a task. So the first 8 registers belong to task 0, and the second 8 registers belong to task 1, at least according to gimme nomenclature. And this allows you to switch between 2 different contexts, 2 different mappings of your MMUs without a lot of hassle. It's very, very quick. You don't have to say, you don't have to load whatever MMU or whatever slots have been selected, save that out, and then restore it later on. You just flip a bit, and you're good to go. So that helps us out. So we're gonna utilize that. Chaos, the framework that I have, the runtime that I use, I actually use both of those. So now task 0, those first 8 registers, those are allocated for the game itself. So typically, chaos will do its thing, the game will do its thing, and all of it runs in task 0. And for task 1, we devote that to our audio mixer. And we do that because you want to be able to have up to 3 channels you want to have a waveform, or or sample data. You need to be able to map 3 different waveforms in. So that's three blocks. You've got all kinds of code that needs all kinds of stuff that has to be done with it. So trying to do something like that um, within the the context of interrupting your game and dealing with that stuff, this is just far more efficient and effective to do. Um, and that, of course, defines a lot of things in the way that chaos works, and that's why those last two MMU slots, those last two register slots, are always the same across both of those tasks, so that I can switch between the two of them, quite easily, quite fast, and not have to worry about anything, and be able to switch between two actual tasks within my game that have completely different memory requirements, completely, and need access to completely different memory. So now, if you're looking there at task zero, you'll see that the first 5 MMU slots are devoted to a context. And what that means is there are different modes of operation, or different things that happen within the game loop. And everything that I'm doing right now really goes through a game loop. It's always going to be running a game loop. So things like rendering, cleaning up the background, drawing sprites, updating, or the game logic, all of that. Each one of those things has a different memory context. Knowing what is and isn't mapped in is important, because if I do have to modify some of that stuff, to map in something different, say I'm updating the game logic, and I've got to map in something for collision detection that is super extra special. So I have to map that in, and then I have to map something else back in. So knowing what is in that stuff and being able to, it gives me a better chance of managing it when I write the whole program. So that actually comes with multiple contexts. There's different ways to define that. So and then the last 3, you've got your application code. You're always going to have code for the application running it in some way, and that's where it's going to be now. You can map in code in and out, but it typically goes through this. And this again is actually turns out to be very, very effective, because you can still devote to, say, slot 4 to code if you really need to. Then of course our shared data and our chaos runtime. So now for this game, I'm just starting off with simple. So our application game logic, the first 4 MMU slots to be determined. We don't know what those are going to be yet. Okay, we have some additional application data that we want in, maybe some collision detection. Who knows? We've got our app code, and then we've got our shared data and chaos runtime. So that's pretty easy. We can work with that. We can expand it. We can evolve it. Now, we're also going to be, when we get started, one of the first things that we're going to do after getting the machine initialized and get the program up and running is going to be rendering the background, maybe, or maybe we'll do a prototype. I do highly recommend doing prototypes. So we've got a context for that, and if you're doing a prototype, you want to at least try it within a particular context to prototype that too. So we start with, I got to have the frame buffer. At least one block has to have the frame buffer that I'm drawing to. I need to have at least one block mapped in for the tile set. I mean, I've got to have the graphics to draw. I would prefer 2 blocks devoted to a tile map, so I can reduce comparisons, or having to add additional code in there and split up my my unrolled loop to draw an edge. So we want to try if at all possible, keep that in there. If not, then it goes. But we still have one reserved. Don't have anything to do with that. So, but keep in mind, we may have to make some sacrifices, so that might get allocated. And then, of course, application code, shared data, and chaos runtime. Now, for rendering sprites, that's a little bit of a different story, because we aren't really going to be doing any kind of clipping. And even if we were, there's going to be situations where drawing a sprite is going to overlap and move across boundaries of that that 8K boundary for an MMU slot. So we've got two blocks, or 2 slots dedicated to our frame buffer, so we don't have to do anything special, no comparisons, we just draw. Now, if we ever need to remove that, or we never need to reduce that, we can, but that's going to come at the cost of some CPU cycles. Okay, so and we've got to have some place to store our information, possibly the actual background graphics to restore our dirty regions. So we've got, it doesn't matter if that's shared with somebody else, we still have to be able to map that in, and we can't guarantee it any other place. We've got our sprite table, which tells us where our sprites are there. All the one, we might be able to consolidate our sprite table in there, because if we only have 80 sprites, we might have enough space. But we also have animations and all kinds of stuff. So, and then we have our sprite set, which is our actual sprite data. The image and the two textures, the image texture and the mask texture. So we only need one for that. We only really need one for that. So we know that we can't cross those 8K boundaries on that. And of course our application code and shared data and our runtime. Now those having just those context map out, I know where everything is going to go in the logical memory. I know where everything is going to go in physical memory. So when I start writing my code, when I'm gonna draw some I'm gonna draw my tile map, or I'm gonna start doing my tile drawing stuff. I can just go ahead and do it without having to worry about, well, am I putting this in the right place? Am I going to need to change this later on? So, you already know where you're going to put it. You can do all of your prototyping using that. So that way, if you do a prototype and it turns out that, hey, this is worthy of being included, just got to make a couple of changes. You don't have to do a whole lot. And these things are going to come up quite a bit, where you're going to be doing something like rendering tile background. Well, what if I have to map in something special along the way? Rendering sprites. There's all kinds of stuff you could do with sprite rendering that you could require additional data. So you've got that to consider. And of course, you've got the more of a micro view of memory map, because you've got that shared data and that chaos runtime, and there is some data in there that is shared outside of the shared data, of course. So we've got shared data. We've got the chaos runtime itself. I mean, the shared data is 8K. Your runtime is 6K. The stack is 256 bytes. Now, of course, that can shrink if I need to, and very easy to tell if I do need to. 256 bytes for the DAC buffer. This is the buffer that the sound mixer in task 1 fills into play, that gets sent out to the 6-bit DAC. And that's just a simple ring buffer, a circular buffer. It gets to the end, it goes back to the beginning, keeps on doing it. We've got our direct page with the data for the application, which is 160 bytes. We've got a lot allocated for that. And then there's a region allocated for chaos. There is some housekeeping data that it has to keep, so that's where it stashes it. And you've got 32 bytes for the DAC driver itself. That's the actual code that pushes the stuff out to the 6-bit DAC. And then you've got 238 bytes of chaos data. And that's actually outside of the direct page. So of course the state, that's all outside of the direct page, but you do have the interrupt vectors in there. So now keep in mind that this model is actually flawed. There is actually a problem here, because that direct page data actually needs to be up in the FEFF region in order to get a short branch to it, because it is not always setting in direct page. That's something that I'm going to cover in a future video, because there are times where I change the direct page quite often, just like I mentioned with sprites. When I draw a sprite, I've got to draw the direct page. Well, I can't disable interrupts along the way. Still got to play sound, so I just switch over to a version that sits outside of the direct page, but is still in memory, and it's a little bit slower, but at the same time, I'm not going to be using that for a whole lot of the samples. So, and I save a lot more than just not doing that. So anyway, this is something that I will have to change. So and in fact, there we go. It's changed. Yeah, I did a lot of this up and before. So anyway, that's I think that's going to be it for now. I think I've covered all that stuff. This is all the stuff that that I just collect before I get started. And of course, I did go a little bit farther than I normally do this time, simply because I'm pulling details from 3 different generations of the game. There are some differences. There are going to be some challenges. I mean, 144K for a tile map, that's a lot. That's a lot. So it's going to be a challenge to get some of that stuff down and just to get it to fit into memory. And I feel sorry for was the guy, Cedric, doing. I feel bad for him because he's going to have some of these same challenges, and it's going to be rough. It's going to be a very very rough time to get some of that stuff worked out. And he's looking at some of the same requirements I am, except he's going to be a lot more fixed, or a lot more attached to them because of the type of because the game actually kind of requires some of it. But anyway, that's kind of it. I think in the next game, or the next video, uh, we're going to start actually writing some code. I'm going to go through setting up the a state machine, and getting all of that up with some sample data, some sample assets, as many as I can, along with tackling that 144K tile map, that 32K tile set. Those are going to be things we have to work out ahead of time. So we'll look at some of the potential solutions for that. And anyway, until then, have fun.